Hi everyone. So this is an exercise from the textbook. Actually, I pulled this off of WebAssign, but it's very similar to one of the exercises in the textbook. And I didn't go over quite anything quite like this in the main video, so I just figure I'd make an extra video just for this one exercise. And this was by request, so. So the problem is to convert the integral, and it's a triple integral, from rectangular to cylindrical and spherical coordinates, and then to evaluate whichever one you think is easier. And so it's the triple integral. We're going, x is going from -9 to 9, y is going from negative square root of 81 minus x squared to positive square root of 81 minus x squared, and then z goes between x squared plus y squared to 81. Okay, so yeah, before we try to convert anything here to cylindrical or spherical, we might want to figure out what this region is, right? So let's start with just the xy plane. So So we know x is varying from -9 to +9, right? And then y is going from, so these are x's, just to make that clear. And then these are y's, if that helps, right? So essentially y is plus or minus, right, the square root of 81 minus x squared. And I'm hoping that looks familiar to you. If it doesn't, let's do the following. Let's just square both sides, square the left side. And then, of course, plus or negative doesn't matter. When you square the square root, it's the inverse of taking the square root, you just get y squared equals 81 minus x squared. And if I pull the x squared to the other side, right, I add x squared to both sides, I get the more familiar x squared plus y squared equals, well, 9 squared, right, which is 81. Right, so that explains the 9 here. It's the radius of a circle, right? So this is just the equation of a circle of radius 9. So yeah, the top curve here is just the top half of the circle. Let's try to draw that a little bit better here. Okay. So yeah, this is y equals positive square root of 81 minus x squared. And then the negative is just below the x-axis down here. So y equals negative square root of 81 minus x squared. Okay, so right, so for the last two integrals here, this just describes the disk, right? Everything inside the circle here. Okay, now let's look at the z's, right? Z equals 81, well, that should be familiar, right? That's just a plane, a horizontal plane lifted up 81 units from the xy plane. And z equals x squared plus y squared, oops, sorry, that should also look familiar. So I'm going to try to draw the three-dimensional version of this here, if I can. So this will be the z-axis, and way down here will be the xy plane. We'll do it this way, right? So, right, x goes from, let's say, -9 to +9 here, and then y goes from the negative square root, that's the lower half of the disk, to the positive, that's the upper half of the disk. So this circle is just the same as this in the xy plane. All right, so now let's draw the actual surface here. So z equals, the lower surface is z equals x squared plus y squared, right? So notice it's not z squared, right? That would be a cone. It's z equals x squared plus y squared. Right, so that is a paraboloid. Right, you can either look it up, or just, right, if you just get rid of the y squared, z equals x squared is a parabola, right? You know, two-dimensional curve, right? And so the x squared plus y squared just essentially gives you the surface of revolution, right? So you take your parabola here and revolve it around the z-axis. And it should look something like this. Okay? So that is the lower surface. The upper surface is z equals 81, which is just this plane here. Right. Oops, sorry, that's z equals 81. There's no negative sign here. Right. And right, how do I know that this ends up exactly at z equals 81? Well, if 81 is equal to x squared plus y squared, you can tell that this goes, well, this should go straight down to the circle here. So I was off by a little bit. So yeah, essentially this solid region then is everything above the paraboloid but below the plane. So it's this solid region in here. Okay, so so that tells us the region Q over which we're integrating. I'll just call this Q, right? And notice that we're not finding the volume, right? If we were finding the volume, we would be integrating 1 instead of x. So we're integrating x, right? We're integrating some function of x, y, and z. And it turns out to be just x, so it doesn't depend on y and z. And if you're really clever, you should be able to answer, evaluate the integral without doing anything here, right? So what is the answer to this? Right. In my mind, it's obvious. If it's not obvious to you, okay, then let's go ahead and switch to cylindrical and spherical, and then we can evaluate one of those. You could, of course, try to evaluate this integral in rectangular coordinates. Probably not very easy, but it's probably doable. It's just not what I would prefer. So I would probably prefer either cylindrical or spherical. So let's start with cylindrical. I think cylindrical will probably be easier. Right. So this is going to be tough to keep this in view here, but if you remember what cylindrical looks like, it's basically just polar and then the z-axis, right? So it's r theta, and then z is the same as it is in rectangular, right? So you're going to have some sort of a triple integral here. X, of course, in cylindrical, well, again, you should know this by now, but you can also look it up. X is equal to r cosine theta. Okay, so that's what we're integrating here, r cosine theta. And then dz, dy, dx, the Jacobian for that in cylindrical coordinates is r dz, dr, d theta. Okay, so yeah, you need an extra r just as you would in polar coordinates, in two-dimensional polar coordinates. So this is just the three-dimensional version of polar coordinates. Okay, so yeah, we're going to be integrating r squared cosine theta. So let me write this a little bit bigger here now, because we have to put in the limits. And we're integrating r squared cosine theta. And then the usual order is dz, dr, d theta. Okay, so for z, it's going to be the same as in rectangular, right? The top surface is 81, so z equals 81. And the bottom surface is z equals x squared plus y squared. Of course, there's no x or y in cylindrical. Those are rectangular coordinates. But you should know the conversion here. X squared plus y squared is really just r squared. So we're going from r squared to 81. Right? So z equals r squared. After all, the paraboloid, another way to write the equation of the paraboloid in cylindrical coordinates is just z equals r squared. Same as z equals x squared plus y squared. Okay, everything okay so far? All right, now we have to do dr and d theta. So what is r doing? So for that, I would go back to the just the two-dimensional disk up here, right? So it is the disk. We're going from r equals 0, which is the origin, all the way up to the radius of this disk. So what's the radius of this disk? Right? It's not 81, right? That's the z here. If you solve, right, z equals r squared equals 81, you take the square root, right? You get r equals 9. So the radius of this disk here is 9. So r just varies between 0 and 9. Right? So those are the limits for r. R equals 0 to r equals 9. Right. Now what about theta? What is theta doing? Well, it looks like we want the entire disk, right? So we're going all the way from 0 degrees, which is the positive x-axis, right? You go to pi over 2, and you get you get a quarter of the disk. You go to pi, you get half the disk. If you go to 3 pi over 2, you get 3/4 of the disk. If you want the whole disk, you got to go from 0 all the way around to 2 pi. Okay, so theta varies between 0 and going all the way around is 2 pi radians. Yeah, please don't use degrees here. There are some instances where you might want to switch to degrees, but I think we should be comfortable with radians here. Okay, so those are the limits for cylindrical coordinates. All right, and I think this would probably be very, very easy to evaluate. I'm just wondering if we should do the spherical coordinates first and then see which one we should evaluate. Well, let's go ahead and evaluate this. I think of the three versions, rectangular, cylindrical, or spherical. I think the cylindrical is probably the easiest. So let's go ahead and do it, right? So for the outside integral from 0 to 2 pi, we're just integrating the cosine of theta, and nothing else depends on that, right? For the r integral from 0 to 9, we're doing r squared, and nothing else depends on that. Oh, wait a minute. Sorry. Z varies between r squared and 81. So yeah, so that will add an extra factors for the next integral here. All right. So yeah, let's just start on the inside. We'll evaluate this integral, and this is just 1 dz. Just copying everything else down here. Yeah, so when you integrate 1, you just get z evaluated between, r squared and 81. Right? And so that's just 81 minus r squared. Right, and we're integrating from 0 to 9. We already have the r squared here, and now we're just going to multiply that by 81 minus r squared dr. Okay, so now we have to evaluate this inside integral. Not difficult, I don't think. So I guess before we integrate, we should multiply this out. We get 81 r squared minus r to the 4th dr. Okay. All right, so we do the theta one last. Although, if you do it first, you'll get the answer right away. You'll see later this is all kind of pointless what I'm doing here. So let's see. We go from r squared to r cubed over 3. So 81 divided by 3 is 27, right, r cubed. And then when you integrate r to the 4th, you get r to the 5th over 5. So 1/5 r to the 5th. And we're evaluating this between 0 and 9. So when you plug in 0, you just get 0. When you plug in 9, you're just going to get some constant, some number here. And it almost doesn't matter what that number is, but let me break out my calculator and figure this out. Okay, so 27 is 3 to the 3, 9 to the 3 is 3 to the 6, so we have 3 to the 9th. 3 to the 9th is 19,683. Okay, minus 9 to the 5th divided by 5, which is 59,049 divided by 5, which gives us a grand total of 7873.2, right? And all that's just a constant, so I'll bring that outside. 7,873.2. And now we just do the final integral from 0 to 2 pi of cosine theta, which of course is just 0. So this whole thing is 0. So yeah, so let's do this officially. The integral of cosine is sine, and then when you evaluate that between 0 and 2 pi, well, sine of 0 is 0 and sine of 2 pi is 0. So you just get this number times 0 minus 0. Right. So you get 0. Okay. So yeah, so this integral in either form, right, is going to be 0. And this is going to be 0 as well. All right, so pretty tedious, and of course you should have been able to see that because you're just integrating cosine. All this other stuff will just give you some constant times 0. Now, I said earlier that even from looking at the integral here, the triple integral in rectangular coordinates, that it should have been obvious that you should have seen that this is 0, right? And again, if it wasn't obvious, that's okay, because just go through the calculations and you'll get 0. So here's the issue, right? We're integrating x, right? We're integrating x over the disk of radius 9, and it's the entire disk. Now I messed up the disk already, so let me see if I can clear that. Okay, so this, going back to the beginning here, again, the disk here is just x squared plus y squared, well, is less than or equal to 81 for the disk. So, right, we're integrating x. So if you're integrating x from negative 9 to 0, this is where it's going to be negative. X is going to be negative here. And where you're integrating x from 0 to 9, it's going to be positive. So, right, so this is just symmetry, right? Whatever happens on the right here, you're going to get some positive number. And then whatever happens on the left here, you're just going to get the same number, but negative. And so by symmetry here, this should have been, right, it should be somewhat clear that you would get 0 here. Right. On the other hand, if you were integrating, let's say, x squared, then that destroys the symmetry, because now x squared is going to be positive, both on the left side, both on the right side and the left side, and then that would end up with some positive number, right? So yes, it's the fact that we're just integrating x, and x is, you know, both positive and negative across the disk in equal amounts, in equal areas. All right. So yeah, so from my point of view, I knew that this was 0 just because of symmetry. But if you didn't get that, or if you didn't notice that, that's fine, because when you do the calculation, you still get 0. Okay. Now the hard part, now we have to go into spherical coordinates, right? So we did cylindrical coordinates, and we evaluated that. And again, I did this step by step, right? So it made it look like a long, tedious calculation, and it really wasn't. You could probably, you know, if you had to, you can go through and just maybe 3 or 4 steps here. Okay, but now we have to not evaluate it in spherical coordinates. We just have to convert it into spherical coordinates. Right, and so that's going to be the hard part. So I'm going to do that way down here. Okay, so spherical coordinates, right? We have rho, which is the distance from the origin, phi, which is the angle with respect to the z-axis, and then theta is the angle that goes around the xy plane, right? Measuring from the positive x-axis being theta equals 0. And then here's some conversions, right? X squared plus y squared plus z squared is rho squared. And then going from spherical to rectangular, it's just the usual that you have on your formula sheet. Okay, so how do we describe this region in spherical coordinates? All right, so remember rho is the distance from the origin. So if you start at the origin here and you go outward this way, eventually you'll hit the surface. And the surface is, right, z is equal to x squared plus y squared, or z is equal to r squared, right? As long as the angle phi is big enough. If the angle phi is smaller, like let's say it's this angle here, you don't hit the paraboloid, you hit the plane, right? So what is the dividing point? It's going to be right here is where the paraboloid hits the plane. So if I draw that line, okay, pretend it's a line. This is really hard to draw a straight line here. And then to have the 2 points meet. There we go. All right, close enough. Make it a little bit more solid here. Right. So what is this angle here? What is this phi here? That specific value of phi. Okay, so what is r? Right, little r is 9, and z is 81. Oops, didn't need that. So again, this is getting a little confusing. Let me draw this triangle down here, right? So this is 9, this is 81. Right? And then you can calculate what rho is, right? It's going to be the square root of 9 squared plus 81 squared. I have nowhere to put that. Right, I'll just call it rho, let's see, rho L for the limit. So this is going to be the square root of 9 squared plus 81 squared. Again, I don't think we need that. So 81 squared plus 81, it's square root of 6642, whatever that is. Yeah. No, what we really need is phi. Right? What is that angle? So just trigonometry, right? You can use, at this point, now we know what rho is, you can use sine, cosine, but why not use tangent? Because we have opposite over adjacent. Right? So tangent of phi is opposite, which is 9, that's the r, over the adjacent, which is, which is z, which is 81. So that reduces to 1 over 9. Right? So phi is just the inverse tangent or arctangent of 1/9. Okay, so that's our dividing point. So here's what's going to happen, right? When phi goes from 0 to this angle, so this is phi equals 0, and this is phi equals arctangent of 1/9, whatever that is, we have a cone. We have the inside of the cone here, right? And you can see the paraboloid is a little bit thicker than that cone. We do have the region outside of the cone, but inside the paraboloid is this stuff in here. I'd say on both sides, but remember, this is swung around the z-axis, right? So you can think of the cone here is the inside part, and then the paraboloid is just the sort of the bowl on the outside. Yep. So, yeah, so this is not going to be simple, right? We have to divide this into two regions, the cone and then outside of the cone. So the inside of the cone is orange, the outside of the cone is purple. Right. So, yeah. So we have inside cone, and then we have the outside of the cone. Right. But inside of the paraboloid. Okay, so let's do the cone first. So we'll do that down here. So this is the inside of cone, and it's a triple integral. And what are we integrating, right? We're integrating x, which is all of this way over here, right? Rho sine phi cosine theta. Okay, and then dv, right, the dz dy dx in spherical coordinates is rho squared sine phi. Then you get d rho, d phi, d theta, right, in that order. All right, so what are the bounds here? What are the limits of integration? So let's start with rho. Rho is just going from, well, 0 to the upper plane, z equals 81. Right? So rho starts at 0, and then we go to, well, z equals 81. The problem is there is no z in spherical coordinates, right? You can use z in rectangular or cylindrical, but not in spherical. All right, so what we need to do then is to convert z equals 81 into spherical. Well, here's z, right? Z is rho cosine phi. So this is equal to rho cosine phi. Okay? But we're looking for rho, right? So let's just divide by cosine phi. Right? So rho is just going to equal 81 over the cosine of phi. I would prefer to write 1 over cosine. Hopefully you remember that that's just, that that's just secant. So rho is just 81 times the secant of phi. So, right, this describes the plane z equals 81. Right? Because that's the outer edge of the, right, that's the outer limit, the outer edge of this region, right? We're not going to go anywhere above, right, z equals 81. Or in spherical coordinates, we get rho equals 81 times secant of phi. Okay, so that's rho. What about phi? What is phi doing? Well, we're on the inside of the cone, so we certainly start at phi equals 0, and we want to end up at the surface of the cone, which is this angle here, inverse tangent of 1 over 9. So phi starts at 0, and we go to inverse tangent of 1/9. And finally theta. Well, hopefully theta is obvious because we're going, let me get a different color here, we're going all the way around again, right, from 0 to 2 pi. Right, we're not cutting this in half or anything. We have the whole of the unit disk, sorry, not unit disk, but disk of radius 9 going all the way around. So yeah, theta is still going from 0 to 2 pi as it was in cylindrical. Okay. All right, so, right, that's not, we're still not done because that's only the orange part. That's the cone. That's the inside of the cone. We still have the purple part here. That's outside of the cone. It's inside of the paraboloid. Okay, So let's do that down here. So we have to add this, right? We're going to add another triple integral. And the integrand is going to be the same. And in fact, we can simplify this, right? This is going to be, let's see, rho squared. Let me move it over a little bit. Sorry, rho times rho squared is rho cubed. And then we have sine phi times sine phi. That's going to be sine squared of phi. And then cosine theta. Right, so d rho, d phi, d theta. Okay, yeah, same integrand as the inside of the cone, right? We're just integrating x dv, right? So, yeah. So if it's not clear, or if this wasn't clear here, right? This here is your dv. All of this is just x. So in the original problem, right, we're integrating x times dv. But here we had to convert everything to spherical, right? All right, now we need the bounds, and again, that's usually the hard part. So let's look at the picture again. What is rho doing? Well, we're starting at the origin, and we're moving outward from the origin here until we hit the paraboloid. So the paraboloid is z equals r squared in cylindrical. So z equals r squared. What would that be in spherical, right? Because there is no z or r in spherical. All right, well, we know what z is, right? Z is rho cosine phi. We use that already. So this is just rho cosine phi. And what's r? R is rho sine phi. Right, so this is going to be rho sine phi. Right? But it's squared. You're squaring the whole thing. Or just square the rho and square the sine of phi. So I can divide by rho, right? We can divide both sides by rho just because it's not 0, except at the origin. We're not going to worry about that, right? So we end up with cosine phi equals rho sine squared of phi. Okay. And we're solving for rho. So divide by sine squared of phi. So rho is just going to equal cosine of phi over sine squared of phi. So that is the equation of the paraboloid, z equals x squared plus y squared in rectangular, or z equals r squared in cylindrical. Yep, it's a little more complicated in spherical. It's rho equals cosine phi over sine squared of phi. And if it's all the same to you, I would prefer to write this as, let's do 1 over the sine of phi times cosine phi over sine of phi. Right? So this is really just cosecant of phi times cotangent of phi. Okay. So that is the furthest row. So that's the upper limit here. Let me go back to this, right? Rho starts at 0, and we end up at cosecant cotangent of phi. Sorry, cosecant phi times cotangent phi. That doesn't look clear, does it? Let me rewrite that one more time. Cosecant phi times cotangent phi. Okay. All right, what about phi? Well, we're not starting at 0 because that's the inside of the cone. Now we're starting at the surface of the cone, which is arctangent of 1/9. So now that is the lower boundary here. That is the lower limit, arctangent of 1/9. And then phi goes, what is the upper limit of phi? So where do we stop, right? We're starting here at the surface of the cone, and we're just going to continue to go downward, increasing phi, right? Phi is the angle from the z-axis, going downward, all the way until the xy plane. That's where we stop, right? If we go below the xy plane, there's nothing there, right? So the paraboloid lies above the xy plane. And the xy plane is exactly where phi is 90 degrees, or pi over 2 radians. So, yep, we're going from the arctangent of 1/9 to pi over 2. Phew. All right, and then just theta. Well, so theta, again, we're going all the way around the xy plane, right? So that's another 0 to 2 pi, as it was earlier. So there you have it. This is the same triple integral as this was here in rectangular coordinates. This was in cylindrical coordinates. And it's all of this in spherical coordinates. Yeah, so obviously spherical coordinates is probably the most difficult to evaluate. But at this stage, if you're clever, you notice that you're just integrating cosine of theta from 0 to 2 pi again. So that's just going to give you 0. Right? Now, everything else, of course, if you integrate the rho cubed, right, you're going to get something very complicated here. Right? But in the end, because nothing else depends on theta, there's no theta anywhere in the limits or in the integrand here. So whatever, as long as this is finite, it doesn't go to infinity, it doesn't diverge, then you're just going to multiply by 0. So if you were brave enough to attempt to evaluate both of these integrals, right, you have to add them up, but they're both equal to 0, right? So you would end up with 0 plus 0 is 0. Right? And that's simply because of the cosine of theta here, going all the way from 0 to 2 pi. So there you have it. No, I'll leave that as 0 here. So that, right, that is the answer when you evaluate these. So out of the 3 ways to evaluate it, spherical is probably the worst. I wouldn't even try to attempt it. Rectangular is not that easy either, but it's only a single integral, right? It's only, I mean, it's a triple integral, but it's only one. In spherical, you got to evaluate both of these. And then in cylindrical, oh, I'm sorry, in rectangular, sorry, in spherical, you have to evaluate 2 integrals and add them up. In rectangular, you just have the one, but I think it gets a little bit messy here. I think cylindrical is the way to go. That's the way we evaluated this, and we did get 0. I just erased it, but we did get 0 that way. Right, so yeah, this is a pretty difficult problem, and again, it just depends on how well you draw your region here and how well you interpret the inside of the cone and the outside of the cone as 2 different regions that when you add them up, you get the inside of the paraboloid. Yeah, so I hope this helps. So yeah, not an easy problem, but it's, you know, occasionally you just have to kind of get used to the different regions. So paraboloids are not as nice as, say, spheres or cylinders or cubes, but they do come up, and again, when the stranger the surface, the more difficult it is to figure out, you know, how to convert it to, say, spherical, because this paraboloid here is not spherically symmetric, right? The cone is, actually no, the cone isn't spherically symmetric. It's radially symmetric, right? It's symmetric in cylindrical coordinates, and that's why it was probably easiest to evaluate this in cylindrical coordinates. All right. Yeah, I hope that helps. Again, the spherical was not easy. Sorry about that, but they can't all be easy. All right, so that's why I did this exercise. I knew this would be a very tricky one, but I hope this helps a little. And if it doesn't, you know, I would encourage you to try to draw this region on your own and make it look a little bit neater and prettier than mine. But hopefully that works for you.